Okay, so for today, Monday, July 6th, we will be studying two separate unrelated topics. The first one we will take a look at are what's called parametric equations. And then the second thing we'll look at is what's called partial fraction decomposition. It's a heck of a lot easier than it sounds. So don't be intimidated by the names of these things. These are actually, for the most part, I don't want to say they're easy topics. You know, of course, they're easy for me. I'm the math teacher. All right. But I think compared to what we went through the last 2 weeks with some, trigonometry that maybe wasn't so easy. Some of it was, I could tell by your labs and your exams. But parametric equations and partial fraction decomposition sound like scary things, but they're actually pretty doable. All right, and then tomorrow, so I'm going to write T/W. So tomorrow and Wednesday, we'll be splitting another topic, which is very important for Calculus 2 and Calculus 3 on vectors. Vectors are also important for different fields of science, such as physics. I believe you can use vectors in chemistry as well. You can use vectors in data science and computer coding. And I'll actually mention a little bit about data science and computer coding when we talk about vectors on Tuesday and Wednesday, and how vectors can be used in computer science and, or rather data science, when you are coding programs for businesses and corporations that require you to analyze their data. You're not required to do any computer coding, by the way. It will just be an example for those that might have an interest in it, but you do not have to know how to do any computer coding, so don't worry about that. And you won't be tested on it either. Okay, so now let's get into our topic today. Topic number 1, parametric equations. So the word parametric, what does it mean? We know what equations are. So the last half of the word parametric is metric, right? Metric means to measure, okay? And if we look at the first 2/3 of the word, it actually, you could write the word parameter or parameter from that word parametric. So parametric means parameter, which is really just something special that we measure. It's a special measurement, which in this case will be a variable. So let's write out a definition here to first define parametric equations formally. So the formal definition is this. So we let x equal some function of t, and we let y equal another function of t that's different. So we don't want to write f of t for both. We want to write f of t for one of them and g of t for the other. So where, all right, f and g are two functions. So notice these are two separate functions, but we're going to be relating them to x and y. So these are two functions with a common domain. All right, that just means that they have the same domain. So then what we do is, we certainly want to graph these things, so we have to get some points with x and y coordinates to do this. So the collection of points is defined by this, right? So of course we have coordinates x and y, all right? Well, x and y are determined by those two equations, f and g. So the x value is determined by f at t, and the y value is determined by g at t. So this collection of points is going to form a special type of graph. So this is a little different. Typically, what do we do to get x and y? So typically we choose x and we plug it into one equation and we get a y value. Notice here that this is a little different. The x value is determined by not y, but it's determined by f of t. And y is determined by another function with t, some variable t. So we're not plugging x in to get y. We're plugging t in to function f to get x. We're plugging t in to function g to get y. So it's like two separate calculations to get x and y rather than one equation. So these types of equations are going to form special graphs. All right. So this collection of points defined by these x and y values is called a planar curve. And that just means a curve in the plane or a curve on a graph. You could think of it like that. So planar curve just means it's going to be a special curve on a graph. And it's defined a little differently than what you're used to. You'll see examples and it will make more sense. All right, so now what we want to say here, one last part of our definition. The equations which are x equals f at t and y equals g at t, are called parametric equations. Where the variable t is called the parameter. So hopefully you're all still taking good notes. All right, don't slack off even though it's the last week. I know you're probably getting tired of all this. I am too. All right, but make sure, remember, this pre-calculus is your preparation for calculus. So it's important that you have notes that you can bring with you so you can review these things as you go through calculus 1 and then calculus 2. And then if you go on to calculus 3, all right, you'll have these notes for those things to review them on your own when you need to. Okay, now, so notice now we have three variables in parametric equations. We have x, we have y, and we have t. All right, so t is the new thing here, right? We know what x is and we know what y is. We've seen plenty of x and y. Now we have a third variable t. Okay, so let's just talk about this variable t. All right, in a lot of applications, that t might actually be time. So t can represent time, not always, but in many applications, like in physics, it actually might represent time. All right, and then x and y will change with respect to time. So in one way, this is almost like simple animation that we can work with here. It's nothing fancy, it's nothing spectacular like you would see, in a computer, okay? But I'll show you what I mean by animation in just a moment. All right, so one application with time could be certainly animation, but it's nothing fancy. All right, what else could we model here with animation? Meaning you're going to see it move. So you're going to see something on the graph move. So you could look at examples in physics such as motion. So that would be in physics. Okay. All right, so let me show you an example now. What I mean by animation. So what I'm going to do first is use the calculator to just illustrate it, and then we're going to go back to the notes here and actually work some stuff out. So if you want to plot parametric equations on your calculator, you have to hit mode, and then you go down a couple lines to where you see function, parametric, and polar. Remember good old polar from the other week? Well, this week we're going to be using the parametrics. So you got to click on parametric mode and make sure that is set. Radian is always nice, especially if the function is a sine or a cosine. So radian is usually better. But for this problem, we're going to actually use trig. And I'm going to plot the function 5 cosine of t. So notice this button here, you have x, t, and theta, all right, as your variables, and n. All right, they actually correspond to the modes. So like the first mode is function mode. So when you click on this, you'll get an x. But right now we're on the second mode, parametric. So when I click on this, t is going to pop up. Okay, so these 4 letters correspond to the 4 different modes on your calculator. So when you're in function mode, x will pop up. When you're in parametric mode, like we are now, t will pop up when you hit this button. When you're in polar mode, theta will pop up. And when you're in sequence mode, SEQ, n will pop up as your variable. So in case you're wondering why there's 4 letters on that button, they correspond to these 4 modes. All right, so notice here we have a second function to type in. I'm going to type in 5 sine of t. You're going to understand these a little bit more later. In fact, I'm going to go back and I'm going to edit these a little more. Instead of t, I'm going to write 10t. And then for the second one, same thing. I'm going to put 10t inside the parentheses. And before I hit graph, I'm going to just change one more thing in my settings here. You see where the little box is blinking right here on the little, well, see, this function is going to come out blue. But if I click on it, I can do some editing here. So I'm going to change it to this, I think. Yeah. So notice if you click on line, see where it's blinking? I can, in a sense, change the font of the graph. Now I'm going to change it to where I see like it looks like a key, like a line with a circle. All right, I'm going to do that purposely. And then I'm going to scroll down to OK. And now I'm going to hit my window. My t-step will be 0 to 2 pi. And I'm going to type in 0.01 for the t-step. T-step should be really small so you get a better graph. All right, now here we go. Watch the animation. Watch this. Actually, wait, let me stop this. Let me stop it for a second because the window is not the best window. I'm going to go back to window. Let's see here. Oh, the y values. I'm going to make those, let's say -6 and 6. The x min and x max I'll also make -6 and 6. And if you're wondering what I'm doing, don't worry about it yet. I will show you in a little bit. All right, so here we go. Here's the animation with a better window. All right, notice it's tracing out a circle, but notice it doesn't stop. Notice the movement keeps going. It keeps tracing the circle. And that's the parameter at work, that parameter t. So I'm graphing on an xy plane my x and y values, but that parameter t will do something different. All right, it might trace the curve multiple times. All right, it will move in different directions. So notice it's going around counterclockwise. Do you notice that? It's going counterclockwise. I could make it go clockwise if I wanted to. All right, it should be almost done. 1 or 2 more times. There we go. All right, so now that's done. So now if I go back to my equations, and if I just switch sine and cosine here, I'll actually get the movement, the animation, to go the other way. So notice now it's going clockwise instead of counterclockwise. So now it's just tracing out the circle a certain number of times, but this time in a clockwise fashion instead of counterclockwise. So there's a couple things we're going to have to note here about our graphs. We're not just going to graph the graph, we're also going to note on the graph which way it's tracing. Is it tracing clockwise? Is it tracing counterclockwise? Is it tracing from left to right or right to left? So we're going to have to indicate on our graphs the direction that the graph is being traced. Okay? So that's another definition here. All right, so definition. All right, so parametric equations can be graphed in clockwise fashion, counterclockwise fashion, CCW, counterclockwise. I'm going to write L to R for left to right, or R to L for right to left, etc. So we will use arrows. Arrows to denote the direction of the curve which is called, so direction is a nice word because it makes sense, but of course in mathematics we have to use a different word which, doesn't quite, make as much sense as a word like direction. So here direction is called orientation. All right, so direction and orientation have the same meaning. All right, so for example, if we plot on an XY plane a parametric equation which gives us a circle, if this is a counterclockwise circle, we would put arrows on it like this. All right, so counterclockwise orientation. Or if the circle is traced the other way, if it goes clockwise, you would put the arrows like this. And make sure you use more than one arrow, because sometimes the graphs can cross over each other, okay? So to have multiple arrows will make it clear which way the orientation or the direction of the curve is headed, or which way it is traced. So this would be clockwise CW orientation. Okay. Another example. All right, it's not always going to be a circle that's going to be traced. All right, it could be a simple line. Let's say the line goes from that point to that point. Well, here, if the arrows go like this would be a left to right orientation. But I could also sketch that same line so that the animation sketches it from right to left. All right, so I'll give you a minute there to get caught up. Because again, here, the idea here with the parameter, all right, yeah, it's going to help us find X and Y values to plot, but it's also going to help us see motion in the graph, where you can actually show actual motion of objects on the graph. So it adds animation to your graphing. All right, the next thing we're going to be talking about, of course, is how do you graph these? And then we'll talk about how do you write equations for particular shapes. So we will be looking at how to write parametric equations for circles and ellipses. Okay, so of course, parametric equations and the regular functions are certainly related. You can convert your regular function to a parametric equation and vice versa. So there's a lot of things that we can do here with these things. All right, so the first thing we're going to be doing is graphing parametric equations. And these are really easy to graph, by hand. If your graph is something simple like a line or a parabola or a circle. All right. Sometimes the graphs aren't really doable by hand, and you really need a computer or a calculator to do it. But the ones that we're going to do will be easy enough to do by hand. And you'll see on today's lab, the instructions tell you to do these by hand. So when you're doing your lab, make sure that you're not submitting a graph that was made by a computer or an app, okay? Make sure you sketch it by hand to get credit. All right, so let's start with an example. It's best illustrated here by doing an actual example. So let's do example number 1, where we want to graph the parametric equations. X equals 3t squared and y equals 2t on -2 to 2 for t. So first, that interval means we're only going to pick values for t starting at -2 and going up to +2. All right, so no 3s or 4s or higher. So the first thing you want to do, so step number 1 is to, why don't you set up a table of t, x, and y values. Because remember, you have 3 variables, x, y, and t, or t, x, and y, whatever order you prefer. Okay, so let's do it in that order, t, x, and y. And you want to put t first because you're going to be picking values of t. All right, you're not picking x values or y values. You're going to pick the t values, and then you're going to substitute them into these 2 equations to find x and y. So let's start with the first value of -2, and then we'll do t equals -1, t equals 0, t equals 1, and then we'll stop at 2 to satisfy the interval -2 to 2. Okay, so just to show you how we're going to get the first x value and the first y value. All right, so for t equals -2, all right, you take these 2 equations, x and y, all right, so x equals 3t squared. So in this case, it's 3 times -2 squared is 12, right? It's 3 times 4. And then the y value would be the 2t function. So 2 times -2 is -4. And then just fill in your first row there. In fact, I'm going to extend the table a little bit more. We're going to throw in one more column. All right, so hopefully that makes sense. All right, so let's just do one more. Why don't we do for t equals 0? I'll just jump around a little bit. All right, so x would equal 3 times 0 squared, which is 3 times 0 is 0, and y equals 2 times t, or 2 times 0 is also 0. So for my middle row, I'm going to put zeros there. So if you do the rest, if you plug in t equals -1 to those 2 equations, you'll get x equals 3 and y equals -2. If you plug in 1, you'll get 3 and 2. And then in the last row, when you plug in t equals 2, you'll get 12 and +4. Okay, so now before we go any further, I would like to show you, if I may, how to do this much on the calculator. Because, some equations are not as easy as this. You might get decimals, you might have trig values with pi's and things like that. So on the calculator, let's let's reconstruct this table. So again, if you're using your calculator, make sure your mode is set to parametric. Okay, and notice our equation here does not have trig functions, so you don't have to worry about radians or degrees. But make sure you're in parametric mode. So I'm going to clear out my equation, and I'm going to type in x equals 3t squared and 2t. And just like before, if you want a table, we're going to hit not graph, but second and graph. Second and graph. And I'm going to hit delete to remove these numbers I don't want. All right, and notice how here you have t as the first column, just like in your table, because you have to tell the calculator t values, not x values. So if I start plugging in my numbers for t, I get my x and y values. All right, but notice here, it doesn't just say x and y, it says x1t and y1t. All right, so the 1 just means it's the first equation you plugged in. Because notice, if you go to the second part, there's an x2 and a y2 of t. The t just is an indicator that your variable is t for every line that you write out. All right. So again, you would hit second and graph. You type in the t values, and then notice it will give you in blue both the x and the y values computed in both of these equations. Okay, so now let's go back to our notes and let's do the rest of this by hand. All right, so now in the table, I want to add another column because you are plotting x and y values. You're really not plotting t as points, all right, but you're going to use t to figure out the direction of this curve when you talk about the motion or the animation. So all you got to do is take the second and third column and pair them together. So that's the point 12 comma negative 4, 3 comma negative 2, 0, 0, 3, 2, 12, 4. Now also note, this is how we're going to figure out the arrows without even using our calculator. If you go in numeric order here, if we take a look at the interval there, the lowest t value will correspond to my starting point, and then the second number will correspond to my stopping point. So just note that in the table here, we will start at that point, and then the curve is going to travel through the rest of the points that we have here, and the curve will stop at this point here. So this will be the direction of the motion. Okay? So let's see how that looks on a graph. Part 2. So if we have, let's see here. I think a positive x-axis is all we need because if you notice the x values go from 0 to 12. So let's do ones, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 2, 4, 6, 8, 10, 12. You don't have to number every single line there just because there's so many of them. And spacing them out makes it look more organized and neater. All right, and the y-axis is not that big. It only goes up to really 4s and negative 4s. So first, plot the points. 12 comma negative 4 is down here. 3 comma negative 2 is way over here. The origin 0, 0. 3, 2, and then 12, 4. Okay, now remember your starting point, right? So remember, this was the starting point. This is the stopping point. So you see the curve will travel this way. And then using arrows, right, if I start at the bottom, it's going this way around the curve until it gets to its stopping point. Okay? So you have to mark on the graph those arrows. So make sure you include the arrows. All right. And that's for, remember, what's called the orientation or just the direction. Because if you don't do that, then you're missing part of the graph. All right, because remember, a parametric graph really has three things. It has your x values and your y values, which will create the points. And then the t values help you establish that motion, that animation, that direction that the curve travels in. Okay? So again, you can just think of this graph as like a path of some object that's moving around. Okay? All right, let's do a second graphing example. Let me change that back to black. It's easier to see. All right, so let's do an equation that's a little simpler, I guess. So we want a graph. X equals t minus 3, and y equals 2t plus 4 on the interval 0 is less than or equal to t is less than or equal to 2. All right, remember that would just mean brackets 0 and 2. So sometimes you get an interval, sometimes you get an inequality to tell you what t values you're going to be graphing. Now this table is going to be a little easier to construct because it looks like we're going to use 0, 1, and 2 for t. So t, x, y, and then paired x and y. So again, we're going to use 0, 1, and 2 because it's based on this interval here. All right, so again, let me just show you by hand here, you know, when t equals 0, our first value. So if we use the x equation, which is t minus 3, we would do 0 minus 3, which is negative 3. For the y equation, we would do 2t plus 4. Careful with your plus signs and t's. Okay, be very careful with the plus signs and the t's. They can blend. Maybe it's better to use a capital T, I don't know. So then we do 2 times 0 plus 4 is 0 plus 4 is 4. So my first pair is negative 3 and 4. Okay, so if you plug in 1, we'll get negative 2. And we'll get 6. So that's negative 2 comma 6. And then if I plug in 2, I'll get negative 1 and 8. All right, so again, just as a reminder about starting and stopping points. All right, our first value of t is start. All right, and then your last value of t will be your stop. So that corresponds to the first row and the last row of the table. And that helps you figure out that as you plot the points, all right, your direction will go from start to stop. All right, now we have to graph it. Okay, so we only really need the left side, right? So x looks like it's only negative 1s, 2s, and 3s. The y-axis goes up to 8. So let's do 1, 2, 3, 4, 5, 6, 7, and 8. And I guess we'll just label that in 2s. All right, now first just plot the points that we got. Negative 3, 4 is here. Negative 2, 6 is left 2 and up 6, right about there. And the negative 1, 8 is there. Now, this shouldn't be a surprise that this is forming a line segment, because when you look at your parametric equations, there are no exponents, right? There's no square roots, there's no trigonometry. It's all first degree variables, right? T to the first, x to the first, y to the first. So this is going to be linear. And it's forming a line segment. So notice I only graph from the starting point to the stopping point. So which one was the starting point? It was here, right? So that means my arrows should go up like this to the stopping point. All right, and just one little note here. You don't have to write the words start and stop anywhere. Right? You do not have to write start and stop anywhere, not even on the graph. That's just for our notes. This way you can see exactly where, or how rather, I'm placing the arrows on the graph. It's all about just your starting point and your stopping point, and you draw arrows in the direction from start to stop. Okay? So you just draw arrows in the direction from start to stop, but you do not have to write the words start and stop. Okay, so the next thing we're going to look at is doing a little bit of work with the equations. All right, so graphing for the most part is easy as long as the equations for the most part themselves are easy to work with in terms of the numbers. All right, so the next thing we're going to do, and we're going to really split this into two parts. So we're going to be finding the rectangular equation from a parametric equation. All right, so this is something that you're going to be doing in your lab, which is question 2. All right, question 1, you're going to be graphing and showing the orientation on the graph. And part 2 of the lab, you'll be converting your parametric equations into rectangular ones. Okay? So now, just to compare and contrast these. So remember, we just learned how parametric equations have 2 equations. You have x equals f at t, and y equals g at t. Whereas rectangular equations are your regular equations, your x and y equations, where you have y equals f at x. What's the difference between these? The rectangular form has 1 equation. The parametric form that we're going to be looking at has 2 equations. All right. So let's call this first one A. And this one, let's call it B. All right. So the goal really here, so goal number 1, all right, is to go from B to A. Okay. So that's like number 2 on the lab. All right. So we're going to do this goal here before our first group work and break. And then when we come back from that, we're going to do goal number 2, which will be A to B. And that's going to be like number 3 on the lab. Okay? So that's our goal with this. So let's do goal number 1. All right, so what we're going to do, we're going to take that last example that I gave you because that's really easy to kind of understand how this works. All right, and we'll see how it goes. All right, so goal number 1. So to convert B to A. All right, so the step that you have to do is this. So, let me try that again. So convert B to A, and the way you have to do that, since we're going from parametric form, right, so remember B is parametric, A is rectangular, right? So remember parametric is T, X, and Y. Rectangular is just X and Y. So what does parametric have that rectangular does not have? T, right? So in other words, we want to make sure that T is eliminated when we convert from one to the other. All right, so there's no T here. So we're going to be converting B to A by what's called eliminating the parameter T. And the way you do that is essentially this. You solve for T in one equation, and substitute it into the other. And we'll do a very easy example to illustrate this. And then we'll do another one or two where the algebra might be a little more demanding. So like I said, we'll use the last example that I did, which was, so we want to find, or excuse me, not find. Let me try that again. There we go. So convert each set of parametric equations to a single rectangular one. So I'm going to give you a minute there to catch up. All right, so from the previous example there, we have x equals t minus 3 and y equals 2t plus 4 as our set of parametric equations. So following this guideline here, to eliminate the parameter, we're going to solve for t in one equation. So let's take the first equation and solve for t. So we'll call that step 1. So we would get t equals x plus 3, right? Because all you'd have to do is add 3 to the other side of this first equation, right? So t equals x plus 3, and then you take that and you substitute it into the other equation. All right, so and that's all you have to do, and then of course simplify. So we're going to take this and we're going to substitute into the second equation. So we'll get y equals 2 times x plus 3 plus 4. Simplifying a little bit, we get y equals 2x plus 6 plus 4, and y equals 2x plus 10, which will result in our final equation. And notice you end up with a single equation. It's called rectangular because remember x and y, the plane formed by x and y axes, is a rectangular plane. So we call any equation with just x and y's a rectangular equation. And it's a single equation without the parameter t anymore. Let's do another. Let's do some that involve a little more thinking. little bit more algebra. Okay, so how about x equals t to the 3/2 plus 1, and y equals the square root of t. Okay, now there's no rule that tells you which equation you have to start with. So like in number 1, I started with the first equation and solved for t. I could have started with the second equation. Okay, it makes no difference which one you start with. I always say start with the one that looks easiest, because you can solve for t a little more simply by working with the easiest equation first. So to me, I think the second one looks easier. So what I'm going to do is, for step 1, let's solve for t. So it's almost solved. You just have to square both sides. So if you square both sides, you get y squared equals t. Squaring both sides. And then step 2, we're going to substitute into the second equation, right, which is our first equation. So we have t to the 3/2, right? So it's blank to the 3/2 plus 1. So inside the parentheses, we're going to put y squared. All right, because remember here, I solve for t. And then here, after I solve for t, that's where you substitute it. So you get y squared to the 3/2 plus 1. Now simplify that. What's y squared to the 3/2? It's y cubed plus 1. All right. Remember, one simplification rule here with exponents is when you have a power of a power, so you have y to the power of 2 to the power of 3/2, you multiply the exponents. All right. So 2 times 3/2 is 3. And sure, you could leave it like this if you like. Or we could take that a little further, right? We could get y cubed equals x minus 1, and then y would equal the cube root of x minus 1. So take your pick. Choose your favorite equation. That's why the word or is there. You could actually come up with 2 different answers. Okay. All right. Una más. One more. Let's do a trig equation. So if we have x equals 2 cosine of t and y equals 3 sine of t. Now, before we actually try eliminating t, we're going to write down one little note here about how we actually eliminate t's when we have trig equations. So you're going to have to eliminate t using a trig identity. All right, and put in parentheses, not inverses. That's the wrong way to do it. So no inverses for these. So now, which trig identity are we going to use? Can you think of one that includes both sine and cosine? How about the famous cosine squared of t plus sine squared of t equals 1? All right, so let's do that. So if we take this set of equations, we get cosine of t equals x over 2. Just divide 2, right? To divide 2 to the other side, you can isolate cosine. And then sine of t would be y divided by 3. And then what you're going to do is a substitution into the identity, right? So we have The cosine is x over 2. So we're going to substitute that in over here. The sine is y over 3. We're going to substitute it there. But don't forget, you're going to have to square it. So the way that would look is this. You would have x over 2 squared plus y over 3 squared equals 1. Simplifying just a touch, we get x squared over 4 plus y squared over 9 equals 1. Now, when we come back after our break, I'm really going to be emphasizing a little bit more from problems like these with the trig equations. And what I'm going to be emphasizing is taking this a step further and telling me what shape is this equation. Do you remember this equation? Does it look familiar to you? I hope you recognize this form. It's an ellipse. And it has a center at 0, 0. Now, the bigger number there is 9, and it's under the y value. So remember that the major radius is parallel to the y-axis, with length of 3, right? Not 9, but 3, because remember, it's 3 squared. So the radius would be 3, not 9. And of course, the minor radius, well, we know it's going to be parallel to the x-axis, but I'm not going to write it. But we're going to say it has length, not 4, but 2. Okay, but that's something we're going to be focusing more on after break, is describing the shape. And then, of course, because it's a parametric equation, we're going to talk about its orientation, if it's clockwise or counterclockwise. We're going to look at how many times can you go around the ellipse. Remember, there's motion involved too. It's not just an ellipse anymore. It's the motion of some object that's tracing out an ellipse. Can you think of anything that actually does that? What do we know that actually moves in the shape of an ellipse? So what actually, let me go back to black here. So I know sometimes these colors are not as seeable. So what moves in the shape of an ellipse? Can you think of anything? The planets. Okay. And it just keeps going round and round and round the sun, right, year after year. So in a sense, these parametric equations can imitate that motion around the sun in a very simple way, of course. Okay, so now let's stop there and let's do our first group work number 1, where you're going to do on the lab problems 1 and 2, which is really 4 problems because you have a part A and a B for each. And they might take you around 15 minutes to do. So why don't we make this our 30-minute break? Or not a complete break. Make sure you work for 10 to 15 minutes. This way you don't get behind. And this way, you know, the stuff is fresh in your mind. So it'll be a little more doable. All right, so 30 minutes on that. I'm going to pause the video on my screen. Okay, so a little while ago, we talked about the 2 different goals here for writing equations from one form to another form. So goal number 1, we just completed, where we were taking parametric equations and converting them to one rectangular equation. Now we're going to do it in the reverse for goal number 2, going from one rectangular equation with only x and y to parametric equations where you have x, y, and t. Okay. Okay, so let's write down a little bit of information here about how you would do this. So if a curve is defined by y equals f of x, well, that's rectangular. One way of finding a set of parametric equations is simply to let x equal t, or any function of t. So then we would have y equals f at t, because remember we're letting x equal t, so it's no longer f of x, but it's f of t now. So therefore, x equals t and y equals f at t would be one possible set. There are many other possibilities. So now I'm going to give you a minute here to get caught up. This way you can read it, you can write it, and then we'll talk a little bit more about this. Okay, so now why are there many other possibilities? So this is one way to find a set of parametric equations just by letting x equal t. So that's the important part right there. Well, I don't just have to let x equal t, right? I could let x equal t minus 1. I could let x equal t plus 1, or t minus 2, or t plus 2. I could let x equal t squared. I could let x equal t squared plus 3. Does it matter what I choose? Not if you're just being asked to do something like this, where it's not really specific. If you were looking for a specific graph where it was positioned in a certain place, then it would probably matter. But if all you're doing is looking for a parametric equation for a rectangular equation, you can let x equal whatever. So x equals dot, dot, dot. But the simplest one is what's here in the box, is by letting x equal t, and then y would equal f at t. So for example, number 1, let's say we have f of x equals 2x minus 7. So that's a rectangular equation, right? Because it's x and y. Okay. So step number 1, we would let x equal t. That's it. Step number 2, find f at t, which would be, so think about that for a second. What would f of t be? I'll give you a hint. It's almost the same thing as f of x. So it wouldn't be 2x minus 7. It would be 2t minus 7. So therefore, my answer would be x equals t and y equals 2t minus 7. Okay, so I started with rectangular form, and I finished with parametric. Okay. Now, or, say you really love math, and you think the first step is too easy, x equals t. It's like anybody could do that, right? You could do x equals, make up something, you know, be fancy. All right. So how about we do, I don't know, how about t squared plus 2t minus 4? Notice it's just an equation with t's. All right. So then we would have to do f of that, f of t squared plus 2t minus 4. All right. So instead of 2x minus 7, it's 2 that minus 7, which can be simplified down to 2t squared plus 4t minus 8 minus 7 is 2t squared plus 4t minus 15. So therefore, the set of parametric equations corresponding to this set of choice would be x equals t squared plus 2t minus 4, and the y equation would be 2t squared plus 4t minus 15. Okay? Let's do one other possibility. Or I could let x equal, I don't know, how about 3t? Let's make it a little easier this third time around. So then, notice the first step there is just choosing your own little x equation with t's. It can be anything, and I mean anything. I'm just making stuff up here for the first step. X equals 3t. I could have used 2t. I could have used 4t. I could have used 10t, and so on. Okay? So the first step is your own choice. You get a choice. But the second step, you have to do f of that choice. So f of 3t, remember our f of x is 2x minus 7. So f of 3t would be 2 times 3t minus 7, which is 6t minus 7. So this set of parametric equations would simply be those. X equals my choice, 3t, and y equals 6t minus 7. Okay? Or dot, dot, dot. This can go on and on. You can have an infinite number of parametric equations for one rectangular equation of 2x minus 7. Okay? We can have an infinite number of answers to this. Okay? And it all depends on what you choose for step 1. So notice I used 3 different choices, and I ended up with 3 different sets of equations. They look totally different. Well, maybe the first and third look similar, but the second one with all the squares, that looks completely different, but it's still the same f of x. Okay? So example number 1 here was no trig. No trig needed. Let's also make that note. No trig was needed for this problem. So the next example here is going to be where trig is needed. So essentially, trig is going to be needed in particular for circles and ellipses. But it's not limited to just this. Trig can be used for many other shapes But we're going to focus on circles and ellipses for simplicity's sake. Okay, so what we're going to do is look at a couple of examples where we're going to transform the equation to parametric equations. And then we're going to look for a pattern, because all of this that we're going to do here can be represented by really one or two formulas, really easy formulas. So example number 1 under Trig. Oh, also, before I actually do the example, I want to add a couple more things to this. Essentially, what are we going to be looking for also? The circles and ellipses, no big deal. But remember, with parametric equations, we're also interested in the motion of these shapes. We're also interested in the orientation or the direction of these shapes. So we're going to be interested in certainly clockwise versus counterclockwise orientation. How can we get the calculator to trace a circle in a clockwise direction versus a counterclockwise direction? There's a slight difference. Okay? And then, of course, we're going to be interested in the number of times, all right, the shape is traced. Remember at the beginning of class, I showed you that circle that kept getting traced out multiple times? You saw the little animated circle or dot that kept moving around the circle multiple times. That's what we're going to be looking for here. All right, so now example number 1. Let's just start with x squared plus y squared equals 1. So remember, this is something you learned a little while ago, where this is a circle with center 0, 0, and radius 1. This is better known as the unit circle, which you don't need the unit circle chart for this, by the way. But this is a unit circle because that's what a unit circle is. It has the center at 0, 0 and a radius of 1. So now, what do we have here? This is rectangular because it has x and y. What about parametric? How can we parametrize this equation? Meaning, how can we make it parametric? To parametrize means to make it parametric. All right, so remember in the one example before break, we're going to use the identity that cosine squared of t plus sine squared of t equals 1. Remember I told you this identity would be used a lot. You would see it pop up. All right, now what we're going to do is let's bring down the equation. X squared plus y squared, that also equals 1. So what do you think x and y are going to be here in parametric form? There you go. So we could let x equal the cosine of t and y simply equal the sine of t. So that x squared would be cosine squared and y squared would be sine squared. And there's your parametric equations. Okay? Now you might be looking at that saying, well, can it be one or the other? Could we switch it? Sure. What if I wrote the identity like this, where I switch sine and cosine? Right? And then I wrote x squared plus y squared underneath. So here, x would line up with sine, and y would equal cosine. Right? Just because of the way they line up, that's how I would assign them. All right? So either of those are good solutions. But now we're going to learn that when x is cosine and y is sine, or when it's the other way around, like in the second box here, there's one small difference between these two solutions here. All right, there is one small difference. So let's take a look at that first to see what that difference is. So let's go to the calculator and let's just plot these. Okay. So if we have the first set was cosine t and sine t. Okay, and the difference is this. Watch when I plot it. It's either going to go counterclockwise or it's going to trace out clockwise. So what do we get here? Oh, it's very slow. Look at that. Let me stop this and speed it up. That's moving too slow. I don't like that. So let me change my t-step. The t-steps are too small. Let me make it 0.05. Let's see if that moves faster. There we go. So notice it's tracing it counterclockwise. And notice it's a circle with center 0 and radius of 1. Now let me go back, and if I switch sine and cosine, does it make a difference? All right, you're going to get the same circle, but this time watch how it traces. Now it's going clockwise. The first time it went the opposite way. It went counterclockwise. So the difference between the two equations is just the orientation. All right, so the first one here was counterclockwise. Orientation. And when x is sine, we're going to get clockwise orientation. Okay? So just try to remember it that way. When x is cosine, you get counterclockwise orientation. And when x is sine, you get clockwise orientation. Okay, so that's one difference there when sine and cosine switch. It's just going to actually change the orientation from counterclockwise to clockwise. Okay, now let's take a look at some other things here. All right, how about this example here? What if we have a circle with a radius of 4? Or excuse me, a radius of 2. All right, so this will be center 0, 0. And the radius would be 2 because 2 squared is 4. And again, this is rectangular. All right, so let's use one of those trig equations. It doesn't really matter at this point. Let's not be concerned about clockwise yet. So we have cosine squared plus sine squared of t equals 1. Here we have x squared plus y squared equals 4. Now here you want to be careful. Be very, very careful. In the last example, I could have easily just assigned x and y as the cosine and the sine. But I can't do that here. Can you see why? Take a look at the right side. They're not equal. You have a 1 and a 4. In this example, we had 1s. These were equal, so right away I could equate x with cosine and y with sine. So here we can't say that x is cosine and y is sine. We can't say that because 1 and 4 are not the same. So what we're going to do is bring down the first equation. And then we're going to divide the second equation by 4. So I'm going to get x squared over 4 plus y squared over 4 will equal 1. So I just divided the second equation by 4. And I'm going to do one more thing here. This way you can see it a little better. Bring down the first equation again, doing nothing to it. And then the second equation could be written as x over 2 quantity squared plus y over 2 quantity squared equals 1. So now we can line things up. Now we can say that we get x over 2 squared will equal the cosine of, actually, let's get rid of the square. We don't need that. Let me redo that. The x over 2 can equal the cosine, right? Because notice we're comparing the squared quantities. So cosine squared equals x over 2 squared. So you can also equate them without the squares. You can say cosine is equal to x over 2. And then therefore we can say that y over 2 is equal to the sine of t. And then therefore x equals 2 cosine of t and y equals 2 sine of t for my parametric equations. So remember, you have to solve for x and y. We'll do another one just like that with a little bit more work. All right, so let's just go through the steps of that one more time. So remember, in the first step here, when I line up my equation with the Pythagorean identity, cosine squared plus sine squared equals 1, I can't equate the terms for x and y yet because the right side of the equation is not the same value. So the way you do that, how do you get a 1 here? You divide the second equation by 4. All right, so that was my first step. I divided the second equation by 4. All right, and that's what I did in that step there. So that second part there is dividing by 4. And then in the second part, I write as squared quantities. Okay, so I write x squared over 4 as a squared quantity. Okay, I write y squared over 4 as a squared quantity. This way you can match them up with the squared sine and cosine terms. So that if the cosine squared is x over 2 squared, then cosine is x over 2. And if sine squared is y over 2 squared, then sine is just simply y over 2. All right? And then, final step, solve for x and y. All right, example 3. Let's take a circle with a different center other than 0, 0. So x minus 3 squared plus y plus 4 squared equals 100. So this circle here has center 3 and negative 4, and its radius is 10, because 10 squared is 100. And of course, this is our rectangular equation. So let's see here. We take the trig identity, cosine squared plus sine squared equals 1, and line that up with my equation I have to divide the second equation by 100. Why? Well, in order to equate the left side of these two equations, I have to make sure the right side is equated also. And right now, 1 and 100, they're not equal. But if I divide 100 by 100, I'll get a 1 there, as long as I divide the other side by 100. All right, you know what? So I'm going to bring down the first equation. Then I divide x minus 3 squared by 100. Y plus 4 squared gets divided by 100. 100 gets divided by 100, and I get 1. All right. And then, again, just like before, I'm leaving that first equation alone. The second equation I can write as a completely squared quantity of x minus 3 over 10 squared plus y plus 4 over 10 squared equals 1. Now I can equate the cosine with x minus 3 over 10. And I can equate the y plus 4 over 10 to the sine term. All right, now solving for x and y. So we would get x equals, so you'd have to multiply by 10 first. So you get 10 cosine of t, and then add 3 to the other side. For the y equation, you have to multiply by 10, and then subtract that 4, and these are your parametric equations. All right, so now let's see if we can quickly, without doing any of this algebra, do one more example without doing all this work. So what if we have the circle x plus 2 squared plus y minus 1 squared equals 9. All right, so notice the center here will be at -2 and 1, and the radius will be 3. I'm going to give you a minute there to catch up. And then, could you tell me what the parametric equations are without doing any of the work that I did above? Maybe you notice from problems 1, 2, and 3, there's a little bit of a pattern with these answers that we're getting, that we're seeing maybe the radius and the center in the answers. The radius and the center are in those answers. So just think for yourself, if you look at number 2, what was the radius? The radius was 10. And notice that the cosine and the sine get multiplied by the radius. And then the x-coordinate of the center was +3. And notice that +3, of course, is reflected in the x equation as it's added to the 10 cosine. And the y-coordinate of the center is -4. And notice how that is a -4, all right, subtracted, right, to the 10 sine in the y equation. So then using that same exact idea, this would be 3 sine or cosine, doesn't really matter, remember. And the center x value is -2. And then for the y equation, it would also be 3 sine t. And then the y value of the center was a +1, so you would add it on. All right, so in summary, a circle with radius r and center hk in parametric form is, well, 1, if it's counterclockwise, and 2, if it's clockwise. All right, so it's going to be x equals radius times cosine of. Now here I'm going to throw in one more variable at you. All right, we're going to throw in, it looks like a w times t plus h. And y equals r times sine of wt plus k. And then if it's clockwise, the equations are exactly the same, but switch your sine and your cosine. So we would get x equals r times the sine of wt plus h, y equals r times the cosine of wt plus k. So notice the answers are almost identical, right? Or the formulas are almost identical, except the cosine and the sine will have to switch for the orientation. Now what's w here? Where w is the number of times the circle gets traced. And let's do two examples where you're going to tell me what the equations are based on specific information. So example 1. So let's say we want to find a parametric equation for a circle with center 0, 0, radius of 7, the orientation is clockwise, CW, and traces the circle, let's say 20 times. So the information you need is right above there. So the first one, right, is for the clockwise orientation. Counterclockwise, we'll say is CCW, okay? So we need the second set of equations, right? That's the first thing. Okay, now the rest here isn't really that hard to fill in, right? When we do R sine of WT plus H, so that means X would equal, so the radius is 7 times the sine of WT. So remember, W is the number of times the circle gets traced. So that would be 20T plus H. So H would be 0. So therefore, X equals 7 sine of 20T. And then for the Y equation, we would do R times cosine of WT plus K. So it would be Y equals 7 times the cosine of 20T plus 0. So that means the Y equation would be 7 cosine of 20T. And of course, you could graph these and confirm it. All right. So let's not do that for this one because I don't want to sit there and watch this thing circle around 20 times. That would just get annoying to me. So in number 2, we'll graph this one just to confirm it, but I won't have it go around as many times. So let's say we now have a circle with the center at, let's say it is at -3, 1. Let's say the radius is 12. Orientation is counterclockwise, CCW, and traces the circle 4 times. All right, so the first thing you really want to look at is which set of equations do I use? Well, it depends on the orientation. If the orientation is counterclockwise, then I'm going to be using this set of equations up there. So that means your X will be the cosine equation, and the Y will be the sine equation, okay? So let's do it. So X would equal, so R cosine of WT plus H. Y would equal R sine of WT plus K. So remember, R is the radius, H and K are the coordinates of the center, and then W is the number of traces. So simple enough, we would get X equals 12 for the radius. And notice it's not radius squared, it's just radius, right? So it's not 144. Cosine of the number of traces, so it's 4t, don't forget the t, it's not cosine of 4, it's 4t, plus h. Well, h is minus 3 here, so we're going to put a minus 3, not plus 3. And then the y equation would be 12 sine 4t, and the k value there is a positive 1, so we plus 1 to that. Okay. All right, so now I'm going to graph it on my calculator just to confirm it, but I'll give you a minute there to catch up on the writing. Okay, so let's go to the calculator and let's confirm this drawing. So you have to enter in the equations. So remember, first, if you didn't do this yet, make sure you go to your mode, put it in parametric and radian mode. Parametric and radian mode. So we would have 12 cosine of 4t minus 3. And then 12 sine 4t plus 1. I'm going to need to change my window here. So remember, the t min and t max is 0 to 2 pi, which makes sense, like for full circles. T steps need to be small. 0.05 is probably good. I'm going to make my x min and max, I'm going to make it negative 20 to 20. And the same thing for the y min and max. I'm going to make those negative 20 to 20. This way it fits the circle. Remember, it has a radius of 12. So it's going to go 12 up and 12 down from the center. Okay, so if I set it like this, now watch. Here it goes, counterclockwise. Once, here's the second rotation, the third, and the fourth. Voila, and it stops. So notice that little thing disappears after the fourth trace. Okay? And the only difference is if I were to switch my sine and my cosine, it would rotate the other way. All right, so this time it would go clockwise. There's once, twice, 3 times, and 4 times. But notice the shape is exactly the same, right? It's still a circle with the center at negative 3, 1. So if you go left 3 and up 1, that looks like that's about the center right there, and the radius of 12 units up and 12 down. Okay, so now how about ellipses? Ellipses work the same way. Except remember that they're going to have a major radius and a minor radius. Okay, so we're going to have, so we have center, H and K. And remember, there's 2 radii. So we're going to have radius 1 and radius 2 corresponding to the major and minor radii. Okay. All right, so we would say that the parametric equations are x equals r1 times cosine of wt plus h, and y equals r2 times the sine of wt plus k. So notice it's exactly the same thing as a circle, but you have two different radii this time. And that's for counterclockwise ellipses. And if you switch sine and cosine, then it becomes clockwise. Okay. So again, R1 and R2 can represent the major, minor radii, right? The plural of radius. Now, which one is which? Which one's the major and which one's the minor? Well, it depends on which axis is the major axis. So, all right, so it depends on which axis is parallel to each radius, all right? Or which axis is parallel to the major radius. All right, so for example, let's use the rectangular equation. So number one, let's first look at it in rectangular form. So a rectangular form could be an example like, in fact, let's do one with a center at 0, 0, just to make it easier. So let's say we have x squared over 9 plus y squared over 4 equals 1. So remember, it's very similar to a circle here, but you have two different radii, okay? So here in this problem, this would be an ellipse with center 0, 0. You would have a major radius of not 9, but 3, and a minor radius of not 4, but 2, because remember, they got to be squared. And of course, because the bigger number lines up with x, do you remember that means that the major radius will be parallel to the x-axis. So remember that relationship. The bigger number is under x, so therefore the major radius is parallel to the x-axis. Okay. And let's just say for the heck of it, this is counterclockwise. That I'm just making up here, all right? And let's say it traces once. So traces the ellipse once. So what would I have here? All right, I have h and k are both 0 because the center is 0. Now, since the major radius lines up with the x-axis, the major radius would be my r1 because the r1 is in the x equation. And therefore, the r2 would be 2. Okay, so therefore, I would use the counterclockwise equations up here in the top box, all right, cosine over sine. So x would equal 3 times the cosine of, now since the ellipse is being traced once, that means your w is 1. So you get 1t is t plus 0. And y would equal 2 times the sine of 1t plus 0, which is simply 3 cosine of t, 2 sine of t.
说要早睡，只是每天都说，并没有早睡。
Okay, I'll be back in just a second there, folks. I just had to mute one of our students here. Their sound was on. All right, example number 2. So let's say we have an ellipse with center at, let's say, 1, -1. Let's say its major radius is 10, and it's parallel to the y-axis. And then the minor radius, let's say, is 2. Now, we don't have to write what it's parallel to. I think we know it would be parallel to the x-axis. Let's say this goes clockwise orientation. So that means when you trace the ellipse, you'll trace it clockwise. And let's say it traces, how about 40 times? So 40 traces. So that ellipse will get traced 40 times as a result. So what would our equations be? So first, let's look at the orientation. The clockwise orientation would use my second set of equations here, where the sign is the x equation. Okay, so here we would have x equals and y equals. Let's start with the equation that contains the major radius. That would be the second equation, parallel to the y-axis. That 10 would go in the second equation there. Okay, and oops, that should be an R2. All right, so since this ellipse has a major radius parallel to the y-axis, that radius of 10 would go in the second equation with y. All right, times the cosine of 40t. Remember that number there, w is the number of times the ellipse gets traced. So you get cosine of 40t plus k. K is -1, so we get -1 there. All right, now the equation corresponding to the minor radius will be x equals 2 times sine of 40t. And then plus the center there, h, would be +1. And there you go. Okay, so now time for a little group work. Group work number 2. And a little stretch break. So you're going to do problem number 3 on the lab. There's A, B, C, D, and E. Okay? So let me just explain one thing about these. All right, so in problem A is going to be like way back here, long before trig was needed, to right here. So remember the part here where I said no trig was needed? So 3A on the lab is like this. Okay, so go back and visit this part here for 3A on the lab where no trig is needed. But then, right, so 3A is no trig. But then B through, E is trig, like we just did here, okay? So keep that in mind as you're doing this, so you understand that there is a difference there between problems that really require trig and others that do not, okay? So let's say we do, let's see, 5 problems. Let's make them 2 minutes each, so 10 minutes. and then I'll give you a little stretch time. Let's do a 15-minute group work. And then we'll come back and do the last part of our lecture. So I'm going to pause the video. So let me share my notes, and we will start with part 2, which is a much shorter part, much shorter than part 1, called partial fraction decomposition. Now, it sounds really fancy, but it's really a much more simpler concept. So we all know what fractions are. So what we want to first do is really kind of just consider what it is we're doing. So let's consider these two fractions of 3 over x plus 4 and 2 over x minus 3. Those are fractions. All right. And let's consider adding these together. So now let's add these. So we would have 3 over x plus 4 plus 2 over x minus 3. And remember, you'd have to get a common denominator for these, but I'm going to skip that. I'm just going to give you the final answer to this. If you add these together, it's 5x minus 1 over x squared plus x minus 12. So you would need to get a common denominator of x plus 4 and x minus 3. So the way you would do that is you'd have to multiply the top, the first fraction, you'd have to multiply this by x minus 3. So you would get 3 times x minus 3. You'd have to multiply this by x plus 4. So you get 2 times x plus 4. And then combining the terms would give you 5x minus 1. And then the denominator is found by multiplying your two denominators together for that common denominator of x plus 4 times x minus 3. Okay, so we're not really concerned about adding these together. What we're concerned about here is just kind of understanding the meaning of partial fraction decomposition. So the reverse procedure of what we just did, of writing the answer 5x minus 1 over x squared plus x minus 12 as the sum 3 over x plus 4 plus 2 times x minus 3 is really what we're interested in. So this reverse procedure of writing the answer as a sum of two smaller, simpler fractions is called partial fraction decomposition. Where the two simpler fractions, namely 3 over x plus 4 and 2 over x minus 3, those two simpler fractions are the partial fractions. And the word decomposition, to decompose something, means to break it down into something simpler or into something less, okay? So you're breaking down this 5x minus 1 over x squared plus x minus 12 into something a little more simpler, like these two fractions here. So you're decomposing it to first break it down a little bit, okay? And what you're doing is you're breaking one whole thing down into simpler parts. So that's why they're called partial fractions, because each fraction is a part of the whole thing. So partial fractions are just parts, all right? Fraction parts, all right? That when you add them together gives you the whole thing, all right? So you're breaking down one whole fraction into simpler fractions. Okay, so we're going to be looking at two different situations. So number one, so we want the partial fraction decomposition of P over Q. And just think of the expression here that we just looked at. The 5x minus 1 would be our P, and the x squared plus x minus 12 would be your Q. Okay? So we want to break down an expression like that when Q can be factored into non-repeating linear factors. I'll explain what that means with an example. So I'll give you a minute there to catch up. So let me bring that back down. Catch up for a minute on your notes. Okay, so what does this mean? That the denominator Q can be factored into non-repeating linear factors. So an example would look like this. Suppose our numerator is, well, in fact, the example above is a perfect example. So like if we take that 5x minus 1 over x squared plus x minus 12. So here, remember, we're focusing on Q. Q is the denominator, and we want to factor it. So if we factor this, we get x plus 4 times x minus 3. These two factors of x plus 4 and x plus 3 are non-repeating because they're different, and they're linear because the degree of each is 1. Right? So x plus 4 is linear because the degree is 1. X minus 3 is linear because the degree is 1. And of course, they're non-repeating. All right. And then, of course, x plus 4 and x minus 3 are non-repeating. Example 2. Let's say we had 5x minus 1 over x squared minus 6x plus 9. So here, when we factor the denominator, it factors into x minus 3 and x minus 3. So x minus 3 is repeating in this case because it appears twice. So we're not going to consider that until part 2 here. So for right now, we're going to be considering the problems where the factors are non-repeating. And then in a little bit, we will switch to the ones that are repeating. Okay, so example. So decompose the following. Okay, so let's say, for example, we have this fraction here, 1 over x squared plus 3x minus 10. All right, well, the first thing we want to do is factor the denominator. So we would get x minus 2 and x plus 5. Okay, now the goal here is to do what? What we would like to do is write this as a sum of two simpler fractions. All right, so we want to write this as a sum of two simpler fractions. Excuse me. All right, so here's how you do it. So we take the problem, we bring it down, and we write it as capital A over one of the factors plus capital B over the other factor. And we don't need any more than that because there's only two factors. All right. If there were three factors, we would need a plus C over the third factor. Okay. Now, what we're going to have to do is solve for A and B. This way we can figure out what over x minus 2 plus what over x plus 5 is the left side expression, or the original problem. So the first thing you're going to do is this. So step one, we're going to multiply by the common denominator. Which is going to be the product of your denominators. So the common denominator is the product of your denominators, x minus 2 and x plus 5. So now we're going to multiply both sides by that. So we get x minus 2 times x plus 5 times the left side, which is 1 over x minus 2 and x plus 5, equals x minus 2 times x plus 5 times the first A over x minus 2 plus x minus 2 times x plus 5 times the second fraction B over x plus 5. Step 2. Simplify a little bit. So notice on the left side, everything cancels. The x minus 2's cancel and the x plus 5's cancel, and it gives me 1. So I get 1 equals. Now how about around the A term? The x minus 2's will cancel, right? So then I get A times x plus 5 plus. So if we look at the B term, the x plus 5's will cancel, and I'll get B times x minus 2. All right, now what we're trying to do here is to solve for both A and B. So what you're going to have to do next is get the zeros of your denominators of x minus 2 and x plus 5. And then substitute them in one at a time. All right, so what are the zeros of x minus 2 and x plus 5? Well, the zero of x minus 2, when you set it to 0, is x equals 2. And the zero of x plus 5, when you set it to 0, is minus 5. And now we're going to substitute these in one at a time. So we're going to substitute them in to this part here from step 2. Okay, so first we're going to plug in x equals 2 to this entire equation. All right, so we get 1 equals a times 2 plus 5 plus b times 2 minus 2. And that's coming from that step there by letting x equal 2. Now, conveniently enough, we get 1 equals 7a plus 0. So then therefore, a would equal 1 over 7. And then here, we'll repeat the same thing again. We'll get 1 equals a times negative 5 plus 5 plus b times 5 minus 2. Now here you don't have to plug in a equals 1 over 7. You can do that. So like this is 1 over 7, which we just found. But it really doesn't matter here because when I plug in the other 0, all this becomes 0. So I get 1 equals 0 plus, what is that, 3b. Or b3, 3b. And then divide 3, I get b equals 1/3. So therefore, the decomposition, which was a over x minus 2 plus b over x plus 5, is 1 over 7 times x minus 2 plus 1 over 3 times x plus 5. Okay, so notice what I did here with the a here being 1/7. I can leave the 1 on top and put the 7 downstairs. So you still see a 1/7 there, and then a 1/3 here for b. Okay, so that was the goal. So we go back, all right, right up top here. I just want to make sure we understand the goal was to take the original problem and write it out like this. Okay, so we had to find a and b, and once you find a and b, just go back and plug them in, and you have your decomposition. So that's terrible. Let me try that again with a better marker. So the part in blue is the decomposition. That's what I want. And as a result of that, I have to do that. I have to solve for a and b, and then I come back and I plug them in, and I have my decomposition completed. All right, let's do another one. Excuse me. All right, so second example. All right, so let's say we have, I just want to make sure I'm not giving you the one from the lab. All right, so let's say we have x plus 4 over x squared minus 3x plus 2. So the first thing you want to do, remember, is to factor the denominator. Factor the denominator. So that gives us x plus 4 over x minus 2 and x minus 1. And notice these are non-repeating. So now remember, the goal here is to now write this big fraction as the sum of some simpler fractions. So we want to decompose it. So we're going to write as a over the one factor plus b over the other factor. All right, I don't need any more terms because there's only two factors. Okay, so let's set this up. So we would have x plus 4 over x minus 2 times x minus 1 equals a over x minus 2 plus b over x minus 1. So again, the goal here is to find a and b, and then go back and you'll plug the a and b values in, and then the part here with the a and the b is the answer once you get the values. All right? So remember, this is what I want. All right, so our common denominator is just found by multiplying your denominators, x minus 2 and x minus 1. So this is where now you have to multiply both sides by your common denominator. X minus 2 times x minus 1 times the left side, x plus 4 over x minus 2 and x minus 1 equals, take the common denominator to the left, to the right side. So I just multiplied the common denominator to the a term plus the common denominator multiplied to the right side, b over x minus 1. And now, once you do that, simplify all that stuff. Lots of simplifications happen in that step. So don't try to solve for anything yet. Simplify, because it simplifies nicely every time. So like on the left side, the x minus 2s and x minus 1s cancel, leaving me with x plus 4. On the right side, with the a term, the x minus 2s cancel, and I get a times x minus 1. Plus b times x minus 2. The x minus 1s cancel. And now the zeros of the denominator. All right, so you would have x minus 1 equals 0 and x minus 2 equals 0. You don't have to do that for x plus 4. X plus 4 was not in the denominator, so just take the zeros of the denominator only, not the numerator x plus 4. So here we get x equals 1 and x equals 2. All right, and remember, what do we do with these? We substitute them in to find a and b. So you substitute in 1 first. So we'll let x equal 1. So we get 1 plus 4 equals a times 1 minus 1 plus b times 1 minus 2. So I get 5 equals 0. And then here we get b times minus 1 is minus b. So then therefore b is negative 5. And then by letting x equal 2, we get 2 plus 4 equals a times 2 minus 1 plus b times 2 minus 2. So I get 6 equals a times 1 is a plus 0. And there you go, a equals 6. So therefore, x plus 4 over x minus 2 times x minus 1 can be written as 6 over x minus 2 minus 5 over x minus 1. And it's a minus because, remember, the 5 is negative. So this time, the addition can become a subtraction. Okay, so remember the goal up here was to figure out the values for what I want here. So I have my A was 6, so I get 6 over x minus 2. And the B is negative, which makes this a subtraction instead of a sum. Okay. So that would be my partial fraction decomposition. All right, now part 2. Well, I'll give you a minute there to catch up. So this is the part where P over Q is what we want to find, where Q has, let's say it has n repeating factors. All right, so let's say the problem is P over x minus c times x minus c times x minus c n times. All right, so that would be P over x minus c to the n power for n factors. So the way I would have to decompose this, now watch carefully, I would have to decompose this with a over x minus c to the first plus b over x minus c to the second plus c over x minus c to the third plus dot 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 plus some letter, whatever, I don't know, my nth letter, whatever that is, over x minus c to the nth power. So notice when you have the factors repeating themselves, you have to write out multiple partial fractions for them up to and including the power representing the number of factors. So in case that doesn't make any sense, let's do some examples here of just setting up but not solving. So let's say we have 2 over x minus 3 to the 4th power. How would I decompose this? Well, x minus 3 repeats 4 times, right? So that means I need 4 partial fractions. So I need a over x minus 3 to the first plus b over x minus 3 to the second plus c over x minus 3 to the third plus d over x minus 3 to the fourth. All right, same idea. Let's say we have 2x minus 1 over, let's say we had x times, or rather let's do x squared times x minus 3 squared. So let's see. X repeats 2 times because it's squared. X minus 3 repeats 2 times because it's squared. So altogether, I'm going to need 4 partial fractions. I need 2 for the first factor and 2 for the second factor. So I would write this as a over x plus b over x squared. So those first 2 terms take care of the repeating x, and the next 2 terms will take care of the repeating x minus 3. okay? And we add them, right? We add them. All right, now let's do one more example here before I end things, where we're going to set it up and solve. Setting up and solving. Okay, so our example here is x plus 2 over x cubed minus 2x squared plus x. Well, first thing you have to do is factor this. Remember, the decomposition is based on the factors of the denominator, so it must be factored. So first, let's factor this. So in the denominator, we would get a common factor of x times x squared minus 2x plus 1, which can factor even further in the parentheses as x times, this is x minus 1 and x minus 1. So you get x minus 1 squared. Okay, so that's what we're doing there. We're just factoring and simplifying. We haven't even set it up yet. So step number 1, let's set up. So we would have x plus 2 over x times x minus 1 squared. So if we look at our denominator, we have x with no exponent. So x doesn't repeat, but x minus 1 squared is repeating, right? So we would have to set this up as a over x plus b over x minus 1 plus c over x minus 1 squared. We have to do it for x minus 1 because x minus 1 repeats here twice. X is to the first power, so it only appears once. So I don't need an x squared term because it doesn't exist as a factor. All right, now, the common denominator is x times x minus 1 squared. The left side gives it away, right? The left, I don't know if you noticed that in some of the previous problems, is that the denominator of the left side is your common denominator. Now we multiply everything by x times x minus 1 squared times x plus 2 over x times x minus 1 squared. And then x times x minus 1 squared times the a term, a over x, plus x times x minus 1 squared times the b term, and then plus x times x minus 1 squared times the c term. Now, remember, simplify because lots of stuff cancels. So on the left side, the x plus 2 does not cancel, but everything else does. All right? So like all that cancels. Here, x over x will cancel, and I get a times x minus 1 squared plus, in the b part, x minus 1 squared. So the square cancels out the x minus 1. So we end up with b times x minus 1. Right? Because two factors of x minus 1 over x minus 1 cancels out one factor of each and leaves you with an x minus 1 on top. And then in the c part, we can see that the x minus 1 squareds cancel completely, and we get c times x. So the zeros next, the zeros are the denominator. Well, the denominator has a factor of x and x minus 1. So you set those to 0, and you get x equals 0 and x equals 1. So now we're going to let x equals 0 first. So remember, this is where now you go in and you substitute into this step here. So we get 0 plus 2 equals a times 0 minus 1 squared plus b times 0 times 0 minus 1 plus c times 0. So I'm sure you're noticing the reason why we get the zeros of the denominator is because when you plug in those numbers, you get lots of things dropping out. So here we get 2 equals a times 1, so it's a, plus 0 plus 0 is a equals 2. And then by letting x equal 1, we'll be able to find another value, b or c. So then substituting again into up here, we do 1 plus 2 equals a times 1 minus 1 squared plus b times 1 minus 1 plus c times 1. And that gives us 3 equals 0 plus 0 plus c. So therefore, c equals 3. Okay, so notice something here is that we used the 2 zeros already, and using those 2 zeros helped us find a and c. So now to find b, you let a equal 2 because you found that. You let c equal 3 because you found that, and choose another x value. Other than 0 and 1. We used 0 and 1 already. So why don't we use something like 2? Okay, so then we do that all the way up here. So if x is 2, then we get 2 plus 2 equals a, which is 2, times 2 minus 1 squared, plus b, which is what we're finding, times 2 minus 1, plus c times x will be 3 times 2. So I just filled everything. Everything gets filled in to this equation up here. All right, my a and c numbers, and I chose x to be 2. I could have also used x equals 3 or 4 or whatever. I just can't use 0 or 1 again. So then I get 4 equals, let's see here, 2 times 1 squared is 2, plus b times 2 times 1 is 2b, plus 6. So I get 4 equals 2b plus 8. I get 2b equals negative 4 from subtracting 8. And then dividing 2, I get b equals negative 2. There it is. So I get caught up for a moment, and then we'll write out the final answer together. Okay, so writing out the final answer. So remember, we have to set up and solve for what? The A and the B and C values from here. So now we just take our numbers and just put them on top where A, B, and C are. So A over X, A is 2. So we get 2 over X plus B. B is -2, so actually that should change to a minus. All right, so we get minus B. So that would be 2 over X minus 1. And then plus C, which is 3 over X minus 1 squared. Would be the decomposition of our original problem, X plus 2 over X times X minus 1 squared, where you have the X minus 1 factor is repeating. You could break this down into the sum of these 3 fractions. Okay? That's it. So that's where I'm going to end class officially here at 9:17 p.m. That's not too bad. So then your final thing to do here is to do number, was it 5? No, I'm sorry, number 4. Okay, so I'm going to officially end class there. So if you don't want to stick around, feel free to sign off. I will see you all tomorrow at 6 p.m. for our Tuesday lecture. But for those that are sticking around, I'll be here. So again, feel free to ask questions in the chat or use your audio to ask questions.